Okay, I would like to devote this class to the discrete business, which is what I started last time, but there's more to it, and it is a base of could be a base of many of your projects. Um, so you cannot really do any simulations with continuous functions. You know, the computer does not understand these things. It has to have discrete data. So those spreadsheets that we have seen are pretty much what I'm talking about. So it has to be, it is sequences, it's one number at a time, and we proceed from one to the next, if it is a process or a motion or anything like that. So we're going to do that, but certainly we'll start with a little bit of theory of how it sets up and why it makes sense. So just a few formulas would be in order. So you already can see these are the two situations that motivate our development for this theory. Not as much as motivation as an explanation or a metaphor for those notions. And the notions are the Riemann sums and the difference quotient. So difference quotient from before and the Riemann sums from just now. The important thing is to think about both as functions rather than just a single number. So even though as far as every interval is concerned, it is indeed a single number. If you keep doing it for every interval in a row, and suddenly you have a function. Okay, so in other words, we produce a new function from old. Okay, so the only thing is remains in these two representations where that sign that value to be assigned. Okay, so let me start over with Riemann sums. Okay, so we have suppose we have an interval, so Riemann sums. So we have a function y equal f of x, which we know nothing about, and we have also given an interval a b. Okay, and then what we do, we discretize. So discretize f, and well, the whole thing. How we divide into pieces. So as we have done already, we start with a partition. A is equal to x naught, x1, xn, which is b. Okay, so these are the endpoints. Variable length. It is frequently done with equal length, but that is, remember, that's what we started with when we end up computing a limit, and then we divide into n parts, and then n is our parameter. If they're equal length, then the n is the only parameter that we've got, and then we take the limit, and we did. Remember when we computed that area, and then on the parabola. So with variable length, so length of xk plus 1 is naturally simply xk plus 1 minus xk. Okay, so this will be the run. This is a run for each of these. The rise, however, the rise is also will be obvious what is the rise, but it is the question where the value will be assigned, and the value is assigned to sample points. That's where the values come from to begin with, and then we'll see. So sample points, a partition of the interval number 1, number 2, sample points. So C1, C2, Cn, and each of them lie between, like CK lies between xk and xk plus 1. So it is in the kth kth interval. And that's where the value of the function comes from. Values of f are taken at x equal to c1, c2, cn. So it is literally that example of when you look at your speedometer several times every period of time, and you sort of assume that your velocity is equal to that velocity that you observe. Okay, so roughly this, let's make the picture. So AB, say x1, x2, x3. Okay, and then there are more points in between, C1, C2, C3. Okay, and then the graph, I intentionally will put it, how about I put it in pink, to emphasize y equal f of x, that we don't really know what it is. The velocity may be changing, and we sample it. Okay, so we sample it. This is exactly how we sample it. We literally make a recording. We have some kind of a detector. If it is speedometer, it's speedometer. Okay, so and then these are the values. So f of c1, f of c2, f of c3, okay, and then the question is, naturally, is if it is about the speed, then the question is where we are and where have we been. Okay, so where are we at every moment of time? That's the question. The information is limited. Once again, these dots on the graph that we picked, that's the only business that we know about the speed. So if provided f is the velocity, okay, so the partition is given and the sampled values are also given. So where we are, and once again the assumption is, assume that the velocity is constant during each of these time intervals. Okay, so in other words, this is how you would naturally describe that. So you'd do this, okay, and then during every period of time, the velocity is the assumption, is assumed to be equal to that number, okay, and then you just multiply by the length of the time interval. So then the displacement is what is it? F of ck times delta xk, which I forgot to put here. Delta xk. Okay, so delta xk is the length of the corresponding intervals. So displacement during that interval of time, during xk plus 1, is not equal to that, but it is assumed to be equal to if that assumption of ours is correct. So this is best we can do anyway. So if you have one speed, the other speed, well, what is the what best you can derive from it? So then it means that you're proceeding from that point on to compute in a kind of recursive manner your location on and on. Okay, so and that is called the Riemann sum function. So this is the notation. Say, well, let me first make that picture clearer. So once we have these values, the lengths of the intervals are supplied, as well as the the heights of the intervals. Okay, so the heights, this is what I'm observing. So that is literally, my assumption is very much reflected in this picture. The assumption is that the velocity remains the same during that time period. Okay, so once again, constant velocity. Okay, so and then the displacement over each of the period of time is the product of the height of each of these rectangles times the width, which is simply the area. It's certainly convenient to remember that each time period will produce something that resembles a rectangle, and each of them has this area. Okay, and then what is that? Where is our function? So this is not the original function y equal f of x. We're looking for a new function that represents our location. Okay, so certainly knowing from the displacement, we can figure it out from displacement. Okay, and how we just to find the location, add these terms one by one. Okay, so let me do that. So this is what it's going to look like. So suppose we start at location 0. So this is the first two graphs is the same. That is my velocity. And now I'm trying to figure out the location, even though the x-axis is the same, the time. Okay, so I start with, let's suppose I'm starting at location 0, and then where am I? It is I'm supposed to draw. Well, I'm supposed to find out the location during these periods of time. So that's the trick. So these x's, a is equal to x0, x1, x2, x3. These are the question marks. I don't really care what's happening in between, but I want to know where I am as an estimate, where I am at these moments of time. Okay, so these are the question marks, and again, that's another assumption that I make. I start at position 0 just to keep it simple. Okay, so that dot over there is the initial location, and then I add the area. So it's a bit awkward to somehow turn this bar that used to be a bar, and now I turn it to a length. So, but well, this is the best I can do. So this is that area turns. I made a bar out of it, and that will give me the new location. Okay, location naturally on the y-axis. I may have messed up the scale here, because otherwise it doesn't seem like I'm going to fit it. So, so this is the first bar. Okay, and I am right here. So that's the new location. At time x1, I'm at this location over here. Okay, now I add one more term, so that how I would go this way. I already have reached a certain point, and from that point I'm progressing forward. So the new increment is this. Okay, so once again, where does it come from over here, and that way I have yet one more location. So you can see how the function starts to appear one location at a time, and then the last one, once again, this is where I am already. That's the point I have reached, and from that point on, this is longer. I was going faster, so the bar is longer, right? So that's my new location. Okay, so like this. So in other words, the height of each of these little bars is our displacement, computed by that formula over there, and it is equal to every time to the area of the rectangle. Okay, and as you can see, once again, you have some kind of function appearing here. So this is notation that I'm going to use is S stands for Riemann sum from A to X. And function f. Okay, so and once again, it is If at this time I just want to turn away from the recursive computation like this, adding one term at a time, I could have an explicit formula, and it is a familiar formula. So it will be, once again, I'm not going to fit in here. So direct formula for the Riemann sum. It is, after all, the sum of those areas. Will be f of C1 delta x1 f of C2 delta, I forgot this, f of x2 f of k x delta k. Okay, so the sum of the areas of k rectangles. Okay, and that is the total displacement. But it varies. As you can see, I don't go all the way to xn, which is the last one over here, that's xn. But only go to some length. So once again, it is s from a to xk of f for this particular partition. Okay, so for Riemann sum. Okay, so that's a very, very simple formula. Computing your location looks a little bit long, but let's do it once with Excel, so that we can appreciate what it does for us. Okay, so once again, remember, well, Excel is not as flexible as we are, so the intervals will be equal length, and well, that's pretty much it. Okay, so, and the sample points will be chosen to be the right ends. Okay, so all of these, the sample points here, they will be moved to the right end of each interval. Okay, so let me carry it out. Well, let me do it from scratch. So okay, as we always have, I'm gonna have axis here, and I'm gonna have let's say it's velocity, okay, as a function of time. So starting with to keep it simple, with 0, and then the value of h I put here. It will be 0.1 as I like. So it's going to be equal to the previous plus R2C1. R2C1. Okay? And then I could have a few of those. So this is just the time interval. Okay? And now, and now the velocity, well, it doesn't matter. The point of this whole thing, that you don't have a formula behind it. You might receive the data in the form of just a bunch of numbers. Okay, so I'll put here, how about sine? That doesn't matter whatsoever. So this will be RC2. Okay. Okay. Down. Now I can plot my velocity. I plot my velocity right here. Right here. Okay? So this is my velocity. As it's changing with time over 29 intervals, it is increasing, then it reaches the maximum of velocity and then decreases. Okay? That's all there is. So once again, this is the velocity. I even chose, out of all the charts possible, I chose the chart that has bars, so that, remember, that's what we're going to be doing. We're going to be adding these together, as we have algebraically. Now we do it with Excel. Okay. Okay. So now this is location. Okay, so let's start with the location 0 once again, and now we will be computing the next location based on the previous one. Okay, so where am I after 0.1 seconds? it will be equal to the previous location plus what? The previous location plus what? What? Okay. Yeah, well, that's just the time interval. So what is the displacement every time your velocity was okay, well, maybe I've chosen poorly. Let me put location here. Start with 0 here and then equal to. Okay, so well, let's make it slightly longer but easier. I will go with displacement. Displacement. Okay, so nothing here. Okay, so nothing here. So think in terms of intervals. So right now, 0.1 seconds, or rather what we're after is after 0.1 seconds. Where am I supposed to be if my initial velocity was 0? Look at the initial velocity, the initial moment of time, and during the first time interval, the velocity was 0. So where will I be after 0.1 seconds? What's the displacement? Displacement is always the same. Time multiplied by velocity. Velocity by time, time by velocity is the same exact thing. So if you know the velocity, you know the period of time, you multiply, you know where you are. There is nothing more or less to it to say. It's purely what you estimate your progress when you move 5 miles an hour. You'll know you'll be 5 miles ahead after 1 hour, 10 miles after 2 hours, and so on. So if it is half hour, you'll move 2.5 miles, and so on. Okay. So just all you have to do is just multiply the velocity by the time period. Time period being h. So during the first time period, I anticipate to have moved forward by my velocity, this one, and multiplied by h, which is once again R2C1. Okay, so it gives me 0 because initially when at the very beginning I looked at my speedometer, the speed was 0, so I do not anticipate any moving forward during that period of time. But if I expand down, well, certainly my readings have changed, and every time I have a displacement that is not equal to 0. So when in the second line over there, so the velocity was 0.1, right? So this one during in the beginning of the time interval, I measured the velocity at 0.1 miles per hour, and then after 0.1 hours, my progress was, see, this is the answer right here, 0.1. The next one, the speed was 0.2 multiplied by it's 0.2, and so on. Okay, so it's clearly just multiplication of those numbers by 0.1. There is nothing more to it. See, you're just multiplying the velocity by the time period. Time period exactly the same. Velocity is changing. Okay, and then I have the whole thing of displacements, which I can now plot as well. So once again, this one was velocity. Okay, and now I'm plotting displacement. Okay, so this is my displacement, which is slightly out of proportion. Little displacement every time. Okay, now what I do next is now I want to actual location. So in the next one, I put location. So if I know the displacement from now to the next moment, I will know where I'm going to be. Okay? So in other words, I'm just adding these one at a time, starting with 0. So my initial location is assumed to be 0. Okay, and okay, so where am I next? That's location after 0.1 seconds. Where am I? Well, no, it will be still appear to be 0, because to the left the displacement is 0. Our estimate of displacement is 0, and so it will be still anticipated the location to be 0, even though it's just an approximation. But the formula is the previous location plus the displacement. Okay, that's the whole formula. Previous location, just above, plus the most recent displacement, which the one to the left. Okay, so it tells us 0, but really, as you can see, it keeps changing, so that these positive numbers have been added together one by one, and then as you can see, we're progressing forward, even though not at a constant speed, but at some point we speed up and then we're slowing down. So I'm plotting this one now. Okay, so here it's going to be now this time I'm going to plot the dots like this. Okay, so because, well, there is no integration anymore involved, so a summation or areas. So this is where I am. So this is my location as a function of time. Okay? So as you can see, they are more or less aligned with each other, not entirely proportionally, but I think it is more or less the point is made. So the first graph gives you the velocities, and then you simply multiply. What do you do from those velocities? You just shrink the graph vertically, because the time period is only 0.1 second, so they're certainly very short. But then you end up adding them one by one. Okay, that's the last last column and the last graph. As you can see, you can recognize things that we have discussed previously. Well, try to go backwards. Try to go backwards. If this is our location, this is the last graph. If this is our location, do you recognize the pattern of behavior, the relation between this and the first one? That's right. So first we speed up, right? So see how the location is changing slowly first, then it starts change faster and faster, but then you can see a little bit concavity, if I may say so, and then and that indicates the change of velocity. So so ultimately, if you can start with the last function, go backwards, and that will be its derivative, roughly. So this is only approximate, but if you create, instead of 30 points, you make 500 points, you won't see any difference between the points. They will merge together, and you'll have nothing but two curves. Okay, so so that is this is the Riemann sum computed as a function, and it gives me the location versus the velocity. Velocity, displacement, location. Okay, so these numbers are very convenient because they indicate the exact increments of height that we have at the bottom. Okay, so so we build one on top of the other. I try to put it here. Yeah.
Okay, so how do you choose to use the last cell? When you're using Excel, you have your numbers.
Let me
take whatever the previous number is.
Let me first close this. You can hear me. I can hear you. What is it?
So if I enter series, if I enter your number here,
Yeah.
and then I want this number to use this number.
Yeah. You mean how to spread it?
Yeah.
You mark and then push Control D to spread down, or Control R to spread right. Okay?
So
Yeah, you can have as many Oh, that you want the whole column?
Yeah.
Yeah, so you make sure that the one with information in it is at the top of your highlight, and then just pull your mouse down as far as you want. I'm not sure how you do with the laptop. I
want
the laptop a lot.
to take, like, this number stays the same. So for every cell that it goes down, it'll use this number.
No, it's usually you spread out literally down. The way I just did over here is I pick this one. This one had information. I typed in, and then I wanted to copy that formula all the way down. Okay, so what I did was I put my mouse here, and then I highlight all the way down like this. I don't know how you do that with the laptop. I don't think I ever done it before. And then I push Control down. Okay, so well, that should work somehow. Okay, so that last picture is the most descriptive, I think, right here. How we are stacking up those displacements on top of each other to keep finding the new locations. Okay. Now we're going to go in the opposite direction. So this was from velocity to the location. Now from the location to the velocity. So it's just as simple. So let me write it up first. So you see what we're doing here. We're doing a calculus before any kind of limits get involved. So here we're going to be talking about the difference quotient. The setup is similar. Once again, we have a partition. So partition. So we have y equal f of x, or g of x. Let's call it g of x because we are doing different things to different functions. So partition of integral ab first. Okay, so we have then x, once again, a is equal to x naught, x1, xn, which is b, and then what we do is we want to think of g here as the location. So once again, if we want to go with this metaphor, then we're moving in the exact opposite direction, not from velocity to the location, we're moving from location to the velocity. Okay, so then the values that we know are evaluated during these periods of time. So we know g of x1 or x naught, g of x1, g of xn. Okay, so in other words, we in the beginning of each of these time intervals, we look at at milestones. And so to know where we are, and now we want to determine how fast we're going every period of time. Okay, so so what's velocity? What's the velocity? What the velocity has been during each period of time. So let me plot it. So once again, we have an interval, AB, xy. So with some unknown function. But that's not the same function. You want to emphasize, so there will be no confusion. Even the units are different, right? So the location is measured in miles, for example, while this one and the last one was velocity measured in miles per hour, for example. Okay, so otherwise it's kind of similar. So x1, x2, x3. We're not going to be sampling yet. Let's just determine let's determine the velocity, also known as the rate of change, also known as the difference quotient, for each of these intervals. Okay, that is really uncomplicated. Even in comparison to the last problem, it is totally manageable because, well, look at this. We have a bunch of points, and we just have to look at the at the um, at the slopes. So there are the slopes of the secant lines. Once again, G is unknown anywhere but these values. But it's enough for us to draw through these points that are known to draw a bunch of lines like this. A bunch of lines, and think about it. This is these lines estimate our velocity. Okay, slopes of secant lines approximate the velocities during each of these time periods. So it's really easy to write up because then the each of these will be the run, and which one? This one, like this. The vertical one, well, maybe not like this. This one is the rise. This is the rise. So for each of the intervals the computation is transparent. And the result is, that's the good news, is the result is a function. Okay, except where do these values go? Well, let me first write out the formula. Okay, so that is the formula of the function, is the at g of xk plus 1 minus g of xk divided by xk plus 1 minus xk, which is also known as delta xk. Okay, so the difference quotient, the rise over the run, the change of y over the change of x, that is our formula. So we can compute it for every interval, for each interval. So the question becomes now, how do we make a function out of it? And the answer is we use the sample points. We use the sample points even though we're not sampling there. Okay, so let me just point it out. So these are my points, the same, A, x1, x2, and then somehow, and that is pretty much arbitrary at this point, to choose sample points. Like, it could be anything. So C1, C2, C3. So, and then I put it here, C sub k. Okay, so if I'm looking at the very beginning, the very first interval, I have computed, let's suppose I have computed the slope. The slope has been computed. It becomes the value of my function. Okay, so like this. Well, in fact, how about I put a bar here once again. Okay, so you see what's happening. We had two locations in the beginning and the end of this time interval. Okay, based on this, I compute that formula on right, difference quotient or the average velocity, if you like. So simply the displacement, that vertical interval divided by the time interval, which is the length. Okay, the one. And then what do I do to make things fit together? I could just assume that the velocity that I found was constant during that time period, as if there was no curved function y equal g of x, which is unknown anyway, but as if I was moving along this line over here. Okay, so best we know, maybe it's exactly what happened. We don't know. Okay, so we assume that that's the case. That's our assumption. Just like in the previous one, we assume the speed constant during each of these intervals. Okay, and then we have a bunch of values in that manner. So it was positive, by the way. The next one is negative, so I have to here. So it's the value of the function is here somewhere. So, and then it becomes positive, close to 0, and then one more positive like this. So Roughly, that's what creates a new function of y, and this will be this time this will be the velocity. So this is velocity. Y, this is the location. Through the difference quotient construction, I will end up with the location. Okay, with the velocity. Okay, so let me. I think we have enough time to make a quick spreadsheet for this purpose and have a difference quotient computed in the same manner. Just remember the function is different. Okay, so let me start the new one. Okay, so okay, so I put h here again, 0.1 here again. The values of x are the same, just so it's going to be once again 0, and then the next one is the previous one plus our 2c1. Okay, I pick a few of them. Okay, now this will be my location. Okay, function g. Okay, and then I just put any kind of value I want here. I don't know, 1 minus x squared. Okay, equal to 1 minus this one squared. Okay, what happened? Come on, what the hell is wrong with you? Okay, so these are my location. At some starts positive, then becomes negative. I can now insert my formula, my chart. That's not the. I want dots. This one. Okay, so that's my location. Okay, and then what do? I already announced that I will put velocity here. How? I will just be computing the. I will be looking at these 4 values. I will be looking at the increment of y, or location of the change increment of x. Okay, so it is equal to the this minus that. Okay, the numerator, the increment of location divided by the increment of time. Well, actually, I could simply go with the with h, which is R2C1. Okay, so because it's constant. Okay, so down. Okay, so so these are my velocities. These are my velocities, and I plot them too, since we are almost out of time. So here it is. They are more or less aligned, even though out of proportion. Okay, so velocity, as you can see, becomes more and more negative. You're speeding up down like a free fall object, and then the velocity. So this chart is the velocity. Okay, so what remains, we're going to do it next time, is what's the relation between the two. That's the most important thing. It's called the fundamental theorem of calculus. Okay, so I'll just see you tomorrow.